Next, I would like to talk to you about thermodynamic processes, and a very basic notion that we need for that is the distinction between work and heat, and also the concept of forces. Let me start with work. What is work in this context? Performing work means that I vary external control parameters, like the volume or an external field. So if I have a gas in a piston, for example, it's enclosed inside a certain volume. The volume is one of these external control parameters. When I push on the piston, I compress the gas, I decrease the volume, so I change this particular external control parameter. The amount of energy that I transfer in this way is considered work. Now, this is specifically mechanical work. But there are also other types of work which are not mechanical. When I have a system, say a magnet, subject to an external magnetic field, then I can perform magnetic work on the system by changing the external magnetic field. And then by doing so, I effect a reorientation of elementary magnets, and this is also kind of work. This is magnetic work. So more generally, work is any change of energy that is due to changes of external control parameters. What happens to the energy when I vary in time an external control parameter? An answer is given by the so-called Ehrenfest theorem, which holds for isolated quantum systems, but they are possibly driven by varying some parameter of the Hamiltonian. So they are isolated in the sense that they do not interact with another system, say a heat bath. However, their Hamiltonian may depend on external parameters, like the volume, like external fields, which are allowed to vary. So you allow for a time-dependent Hamiltonian. So the system is isolated, but possibly driven. And then according to the Ehrenfest theorem, the expectation value of energy of this system changes in the following way. This change of energy, expectation value, is given by the expectation value of the partial derivative of the Hamiltonian with respect to time. This psi is some control parameter, like, for example, the volume or an external field. I can also write it in this form, that the infinitesimal variation of the expectation value of the Hamiltonian is given by this expectation value on the right-hand side, which I write as a trace of rho, and then I have this partial derivative of the Hamiltonian, which is the Hamiltonian at parameter value psi plus d psi minus the Hamiltonian at parameter value psi. And now I omit here the time variable. Of course, the change of parameter values for psi is ultimately time dependent, but I omit the time variable here, and I just write the change of expectation value of energy in terms of variations of this external control parameter. So another way of writing this, now without time, but simply in terms of the external control parameter, is that this is the expectation value of the partial derivative of the Hamiltonian with respect to psi times d psi. And we said that this change of internal energy, which is due to changes of an external control parameter, that this we call work. And for this, I introduce the symbol W. Now, I don't use dW, but I use this delta symbol. And this is due to an aspect that I will come to later, namely that in contrast to internal energy, work is not a concept that depends on the state, but work always relates to a process and not to a state. And therefore, the amount of work always depends on the specific path on which you go from one state to the other. And for this reason, this is not a total differential. But I will come to that later. This is just a remark at this point why I use a different symbol here. This is the variation of the Hamiltonian, and this partial derivative of the Hamiltonian with respect to a control parameter is sometimes denoted by an operator, let's say x, and which is a force operator. It's a quantum mechanical operator, it's an observable that corresponds to a force, and that's the force associated with the control parameter psi. It's a generalized notion of force, and it's not necessarily the kind of force that you know from classical mechanics. Let's consider an example. Let's say the parameter that you control is an external magnetic field. So you have a magnet, and its Hamiltonian depends on an external magnetic field B. It has this simple form, minus B times the operator of total magnetization. So it's a parameter-dependent Hamiltonian, depends on B. Then the associated force operator, that's the partial of the Hamiltonian with respect to the control parameter, which in this case is B. And this is minus the operator of total magnetic moment. So this is the force associated with the control parameter B. And then when I change the external magnetic field, I perform magnetic work on the system. And the amount of work that I perform when I change the external magnetic field, that is, according to this formula, it's the expectation value of the force operator, which in our case is minus the expectation value of the total magnetic moment, times the variation of the external control parameter, dB. And this in turn allows us to say, I think we've seen this before, for a magnet, paramagnet, you have this formula for the internal energy. It's minus B times M. This implies that the differential of internal energy, that this is minus M dB minus B dm. You see, it consists of two parts. Energy can change due to variation of the external field, dB, and also due to variation of the magnetization, dm. And you see that this first part here, this minus mdB, this is the work part. So this is the change of internal energy due to magnetic work performed on the system. And then obviously the remainder, the minus BDM, must be something else. And this something else is heat. More generally, the change of internal energy of a system, du, and here I write a total differential, I write a d, indicating that this is a total differential, and the quantity u depends on the state only. It's a property of the state. And when I go from one state to the other, state 1 to state 2, then the difference of internal energies of the two states will only depend on these two states. It will not depend on the precise way in which I went from 1 to 2. All right, so this is the change in internal energy. The internal energy is the expectation value of the Hamiltonian, so it's the trace of density matrix times Hamiltonian. By product rule, you can simply decompose that into a trace of rho times variation of the Hamiltonian plus a trace of change of state times the Hamiltonian. The first part on the previous page we identified with work. So the first part, this is the work contribution, delta W. This is the contribution of work to the change of internal energy. There remains this other contribution, and this remainder, this is what we call heat. And we denote it by a delta Q. And in these two cases, we write a delta rather than a D to indicate that this is not a total differential. The values do not depend merely on the initial and the final state. It's not that you can attribute to a state a heat. You can say the system is in a certain macro state and it has a certain internal energy. But you cannot say the system has a certain heat or the system has a certain work. Heat and work refer to processes going from A to B. And hence also infinitesimal work and infinitesimal heat are not total differentials, but they refer to processes, yeah? And they depend on the path on which you go from one state to the other. I will come back and have a closer look at this path dependence after this page. So you see that while work is change of energy due to changes in the Hamiltonian, which in turn is due to changes of the control parameters, heat is change of energy that is due to changes in the state, and hence changes in the probability distribution of the microstates. Now let's see if we can recover the familiar expression for heat, namely that delta Q is TdS, temperature times change in entropy. Let's try to derive that under the assumption that we are working with canonical states. So let's say the system is in equilibrium, more precisely in a canonical state. And let's assume that the system is in a canonical state at the beginning and at the end of a process. Then, according to our general definition, the heat provided to the system is given by this trace of delta rho, so the change in statistical operator between initial and final state, times the Hamiltonian, which in this example we assume to be fixed. Yeah? We assume that the Hamiltonian does not vary in the course of this process. So this also implies that there's no work involved, but only the state changes. And then the heat is given by this formula. Now, what is the change of statistical operator? It's the final macro state, which is a canonical state with temperature beta plus d beta, minus the initial state, which we say is also canonical state, with some other temperature beta, times Hamiltonian. We can write that as the partial with respect to beta of this trace rho of beta times Hamiltonian times d beta. This trace, is nothing but the internal energy, U. We can use the chain rule. We can write the partial derivative of U with respect to beta as the partial of U with respect to S, with respect to entropy, times the partial of S with respect to beta, and then we have times d beta. Well, we can do that so easily here because we assume that the microstate is characterized by a single thermodynamic variable only, namely the energy, and we don't have any other thermodynamic variables here. So we don't have to worry here about other variables that have to be kept fixed when we take the partial derivatives. It's all easy. In fact, I might not even have to use partial derivatives here because we have one variable only. It's a one-dimensional state space for the microscopic states. Anyway, the partial derivative of the internal energy with respect to entropy, we know that this is the temperature. And the partial with respect to beta times d beta, this is nothing but the differential ds of entropy, assuming that there are no other thermodynamic variables involved. So this is indeed nothing but TdS, the familiar formula. And you can generalize this, so this was just a very simple example with only temperature as the only Lagrange parameter. You can generalize that to situations with multiple Lagrange parameters and recover this formula for the heat.